In this lesson, we're going to examine something called a trig identity. The idea behind a trig identity is to simplify an expression involving trigonometric functions, sine, cos, tan, secant, cosecant, cotangent. An identity is something that, yes, simplifies it, but it has to be something that's true for all values of an angle. So for example, you could choose any angle you want to, and you can show that sine of theta divided by cos of theta always equals the tan of theta. For instance, if we chose just for fun, theta was 45. You could try a calculator here and see what happens. So the sine of 45 divided by the cos of 45 always comes out to 1. Tan of 45, also 1. Okay? Now, I'm only picking one example here, but it should be true for no matter what value I pick. If I tried 30, if I tried 60, if I tried weird things, 53.1 degrees, it would be true that for every number I chose, sine theta divided by cos theta always comes out to tan theta, which tells me that this expression is an identity. Whenever I see sine divided by cos, I can replace it with tan, or vice versa. That's going to be our objective today, simplifying expressions involving sine, cos, and tan. Okay. We can also prove identities. Now that's useful so we can figure out other shortcuts and replacements, even if without having to use our calculator. I don't want to have to go through and touch every value and just to check to see if it works. I want to be able to prove it. And I'm going to do that using some Sir-Sixer ideas. So, using ratios, x, y, and r, we want to prove the following. So sine x should equal 1 over cosecant x. Can we prove that? Well, what do we know about sine x? Sine x is y over r. And what do we know about cosecant x? Cosecant is the opposite of sine, so it's r over y. So I'm replacing my ratios with the letter versions of those things. So can I prove these two things are equal? Sure I can. 1 divided by r over y, and a better way of writing that is r divided by y. And we know that when we divide fractions, we actually want to flip and multiply. And 1 times y over r, well, that's y over r. So I've proven that these reciprocal ideas actually are true. Left side equals right side. This is my proof. Now it's a simple one because it's something we already know. We know the reciprocal idea. How about a more complicated version of that? Sine squared plus cos squared comes out to 1. Can I prove that? Well, sine squared theta is the same thing as saying sine theta squared. And so is cos theta squared. What do I know about sine? Sir-Sixer text tells me it's y over r. So if I square it, and then I do the same thing with cos, x over r, I get this. Well, how do exponents work on fractions? We apply it to the top and the bottom. How do fractions work when I add them? I can rewrite it as y squared plus x squared over r squared. And if I were to just flip that format around for just a second, can I write it in a different format? We might recognize that we've seen x squared plus y squared before. Isn't that our idea of Sir-Sixer that x squared plus y squared makes r squared, the radius of our circle? So I can actually replace x squared plus y squared with r squared. We're saying they're equal. So on the top I have r squared, on the bottom of r squared. Whenever you divide something by itself, you get 1. So I've proven that sine squared plus cos squared equals 1. That way, whenever I see it down the road, I can take something that looks really complicated and replace it with something much easier, a number. My idea of an identity. Okay, you guys to try one. Sine x times cos x times tan x equals 1 minus cos squared. So we can use Sir-Sixer again. What do we know about sine? Sine is y over r. Cos is x over r. Tan is y over x. Y. Cos squared, that's x over r squared. Okay, what can I do here? Well, back to rational expressions for a second. We know we can cancel things if the same thing appears on the top and the bottom. So I can cancel an x with an x. What will that leave me? Well, multiplying straight across the fractions, we'll get y squared over r squared. On the right side, I have x squared over r squared. Those aren't the same things. I want to simplify this. Well, this time if I work on the right-hand side, leave my left-hand side alone, I want to subtract fractions. How do I do that? I make a common denominator. So I got to make it into an r squared x. And if I times this by r squared, I got to times this by r squared. So I hope you would agree with that. Now, I have fractions that are being subtracted, so I can make a common denominator. And r squared and x squared, well, that kind of reminds me of the last one we did a second ago, right? We had this expression, x squared plus y squared equals r squared. Or, if you want to, could we not rearrange that? That looks like what I have. So, if I have that, can I not replace r squared minus x squared with y squared? And I've proven it. I've proven that whenever you multiply sine times cos times tan, you can replace it with just 1 minus cos squared. Now we can go through and prove every identity this way. There's nothing wrong with this, but there's a lot of letters involved here, and sometimes that makes things a little confusing. So we're not always going to use the letters. Sometimes we'll just use the sine, the cos, and the tan themselves. So our objective today is to make complicated things simpler. As, for example, we said whenever you get sine squared plus cos squared, you get 1. Well, let's replace it with 1. And once we've established a proof, like that one, we can use it to establish other proofs, like we did a second ago. And yes, we could use x, y, and r, but we're going to try and get away from that because it often makes things more complicated. We're going to try and work with sine, cos, and tan. So, using our trig ratios, can we prove that sine x, cos x, tan x is 1 minus cos squared? So, how do I go about doing this? This is the same question we just did a second ago, but we want to do it in a slightly different way. So what are some things that we've proved right off the bat already? We've proven that sine x over cos x is tan x. That's a proof we've made. I can use it other places. I've also proven that sine x plus cos squared x equals 1. A second one. And these are pretty much our two handiest identities that we've used already, we've proved already, we can use them to prove other ones. So, if we take this over here and I work on the left side. On the left side, I see sine x, cos x, tan x. But what do I know about tan x? I know tan x itself can be replaced with sine x over cos x. Okay. And then I know I can simplify things if I have the same thing top and bottom. Well, I have a cos on the top, a cos on the bottom, they're multiplying. Let's cancel them out. And I'm left with sine squared. Now, what do I know about sine squared? So here's a tricky idea. This identity can be rearranged like we did x squared, y squared, r squared. I can also use it sines and coses and 1s. I hope you would agree that I can bring the cos squared over. That kind of looks like what I have over here in my question. So I can replace sine squared with 1 minus cos squared. And what did I want in the beginning? I wanted to prove that that's what I had. So I've proven that the left side equals the right side by using my two little identities. That would be these two over here, in a slightly different form, obviously. But now I can prove just using the trig words, as opposed to x, y, and r, that these two things are equal. Okay, so some other math ideas we're going to be able to use. So yes, we can replace. We can also work with fractions. We can also work with factoring and foiling. So we're going to practice some of these things. Can you simplify this by adding? How do we add fractions? To add fractions, we need a common denominator. I need to make them both the same. Now sine squared and cos squared are very different. So to make them the same, we can multiply them together. Just like if I want to make a common denominator between these two things, I would say, well, 4 times 31, that's my common denominator, 124. So we're going to make a common denominator of sine squared, cos squared. Sine squared, cos squared. Whatever I do to the bottom, I got to do the top. So we're multiplying this one by cos squared. So multiply the top by cos squared. Multiplying this one by sine squared. So multiply the top by sine squared. When I have fractions being added, I can join them together on top and make my one common denominator in the bottom. And I hope you recognize that on top is a familiar looking thing. That kind of looks like sine squared plus cos squared. And what do we know about that? We know that's 1. So a simpler expression for these two fractions, instead of having them as two separate fractions, we can join them together to make one single fraction with a common denominator, like we would do with numbers. All right, other ideas we can do. We can expand things. How do we expand? Oh, we multiply. Cos x times 1, that's cos x. Cos x times cos x, that's cos squared x. Totally fine. The same way we've done algebra, we can do with trigonometric things. I can't really simplify that one because they're not like terms. This has a squared, this does not. They cannot be added together. Okay. How about this idea? We can FOIL things. Sine times sine is sine squared. Sine times 1 is sine x. Inside plus sine x. Last, minus 1. We can simplify. Sine squared x, these two will cancel each other out, and minus 1. Okay, so these are some ideas. We can also factor things. And look at this first expression here, and I say, hey, those have the same terms, or there's a common factor. If I take out a sine x, I'll be left with a sine x plus 1. So it's the opposite of the previous thing, right? Here we expanded, and here we're going to factor. Yeah, but look at the next one, 1 minus cos squared. That hopefully looks like the idea 1 minus x squared, a difference of squares. 1 minus x, 1 plus x. I can do the same thing just with trig. So difference of squares, 1 minus cos x, 1 plus cos x. Same terms, opposite signs between your two things. And I can even do more tricky things. I hope this thing to you looks like maybe 3x squared minus 6x plus 3. How would we factor that? We start by common factoring. You can divide them all by 3. And the only difference is instead of having x's, we have tan x's. What am I left with? Well, it looks like a simple trinomial in the middle. Can we find things that add to negative 2 and multiply to 1? Sure we can. Tan x minus 1 and tan x minus 1. Okay, so all the rules that we can apply to numbers and algebraic expressions, we can also apply to trigonometric expressions. And sometimes this will help us simplify things because we might be able to cancel, we might be able to add up, collect like terms, all kinds of good stuff. All right, here's our basic identities. I'm going to give this to you guys as a handout. You don't have to write them all down. You get to use them. Okay, so we know the ones we're really familiar with should be our reciprocal ones. Okay, we can use either version of them. So sine and cosecant are opposites. You flip them over. Same with secant and cos, and same with tan and cotangent. Okay, we've proven sine over cos is tan. Well, the reciprocal is also true. So if you flip tan over, you get cotan. If you flip tan, well, then you flip tan, right? Sine over cos becomes cos over sine. And then the other one we proved, sine squared plus cos squared is 1. And we have some handy rearrangements. So just taking that equation and rearranging it. Those things are really helpful for us. I'm not going to expect you guys to memorize these. We're going to you get them for the test. I just want you to be able to use them. Okay, last idea, I think. So we want to state some, oh, I got one more after this. Equivalent expressions. So give me something that's equal but different for each of these. So if I came across tan squared, what's another way I can write that? Well, tan squared means tan squared, right? And what do we know about tan? Well, one option is I can write that as sine over cos, but it would have to be squared. Another option you could do is that could be 1 over cotangent squared, because that's what tan is. So you have two options here. Those are something equivalent but different. And in either case, we'd probably write these as sine squared over cos squared, or 1 over cotangent squared. Okay, we have to put the square between the expression and the x. Okay, give me something different for sine squared. What can I write that as? Well, I could use the reciprocal idea, so 1 over cosecant squared. Or, if I use the Pythagoras idea, that would be the sine squared plus cos squared equals 1. I could write sine squared as 1 minus cos squared. Those are different things that are equivalent. An easy one, 1 over cosecant. What can I write that as? Well, that's a reciprocal one. I could just write that as sine. There's not really a whole bunch of different versions for that one. Okay, how about 1 minus sine squared? Well, that looks like this Pythagoras idea again. So if I rearrange that one, that would be the same as saying cos squared. Or I suppose if you wanted to, it's probably a little bit messier, but you could write this as 1 minus 1 over cosecant squared, using the reciprocal idea. I would say it's the messy version. I probably wouldn't use that one. All right, how about cos times 1 over secant? Well, cos is cos, but 1 over secant, isn't that itself cos? So I have cos times cos, or in other words, cos squared. Or vice versa, I could change the cos into a, oops, sorry, I should say the word secant there. 1 over secant. Well, 1 over secant times 1 over secant is 1 over secant squared, which these two things are totally related to each other, right? They're the reciprocals. They're both squared. And then the last one, cos times tan. What do I know about tan? Tan is sine over cos. And if I have things on the top and bottom that are the same, I can cancel. So this is just the same as saying sine. Okay, so we've created different versions of this expression. They're equivalent, they're just different. Hopefully in most cases they're easier. I hope you look at some of these things and say, well, it's gotten smaller or it's gotten less part or things like that. All right, here's our last idea. We're going to prove some stuff. Okay, to prove an identity must be true, we have to show that the left side equals the right side, but you can't change sides. You can't move things from left to right or vice versa. Where they start is where they end. So I want to prove the first one. And we're going to do this using sines and coses and tans. We can add fractions, subtract fractions. We can factor, we can FOIL. We just can't move things from left to right. And for the most part, we're going to prove things using our basic identities. So the three big ideas is get rid of reciprocals, make them easier, make them sines and coses if you can. We'd also like to get rid of tan if you can. Use sine and cos. It's way easier. Okay, so let's try the first one. I see it. Oh, and the third idea, work on the more complicated side. Okay, so on this first one here, the left side's more complicated. So what can I do on the left side? I see tan. I want to get rid of tan whenever I can. I'm going to turn to sine over cos. I see things on the top and the bottom that are the same and they're multiplying. Cancel. What am I left with? Sine x. What do I want? Sine x. So I've proven the left side is the right side. I'm done. That's my proof for an identity. Okay, that was a nice simple one. I'll try one slightly more challenging. Last one here. So which is the more complicated side? Well, the left side. If I can, I want to get rid of reciprocals. So I look across here and I see there's this reciprocal right here. So let's fix that. 1 plus 1 over cos. That's what secant is. Okay, what can I do next? Well, next I'm going to use my idea of I can multiply in. Okay, so that gives me cos x plus cos x over cos x. And all that's being multiplied by cos x minus 1. I can simplify this a little bit because cos x over cos x is just the number 1. Okay, where can I go next? I've seen two pairs of brackets being multiplied before. We call that FOIL. So cos times cos, that's cos squared. And then we do the outsides. So cos times negative 1 minus cos plus cos minus 1. Okay, if I collect the two things in the middle, they disappear, right? So I get cos squared x minus 1. Ah, but I want negative sign. So what can I do next? Now here's your tricky idea. We know that sine squared plus cos squared equals 1. Or in other words, cos squared equals 1 minus sine squared. So I can take cos squared and replace it with 1 minus sine squared. So I'm taking this and replacing it with this. I got the minus 1 at the end. If I collect my 2 minus 1, or my 1 minus 1, I end up with negative sine squared. And that's what I wanted. So my left side is my right side. Okay, so that's our intro to identities. We're going to spend 3 days on this topic. The unfortunate part of identities is there's no process to follow. You kind of need to think. What if I do this, is it going to help me? If I do this, is it going to help me? And sometimes it will, and sometimes it won't. You might get through 4 or 5 lines, and I'm going round and round in circles here. This isn't working. And you might need to start all over sometimes. All right, we're going to try a few questions for our homework tonight. And if you're stuck, come see me.